Hello, today we are going to see numericals based on laser. Let us begin. Calculate the coherence length of a laser beam for which the bandwidth del nu, bandwidth is denoted by del nu, is equal to 300 Hertz and speed of light is 3 into 10 to the power 8 meter per second. Here we are going to find coherence length. The formula for coherence length is equal to L is equal to tau into C. Before that we should know what is coherence time. So the formula for coherence time is tau is equal to 1 upon del nu is equal to 1 upon 3000, which will give you 1 upon 3 into 10 to the minus 3 second, and then later on you can substitute the value of tau in coherence length formula, that is L is equal to tau C. We already found tau is equal to 1 upon 3 into 10 to the power minus 3 second, and C is the velocity of light. It is given 3 into 10 to the power 8 meter per second. So the answer is coming out to be 10 to the power 5 meters, or in terms of kilometer it is 100 kilometer. Calculate the energy and momentum of a photon of laser beam of wavelength 6328. So here we are going to find the energy and momentum. It is given. First you need to write the given lambda. Wavelength is given, means lambda is equal to 6328 angstrom degree, but we will convert it into meters. So it is 6.328 into 10 to the power minus 7 meters. Now first you need to find the energy of the photon. We know the formula E is equal to h nu, where h is Planck's constant and nu can be written as C by lambda, because lambda is given, they are not given here the frequency. What is given is lambda. So in terms of lambda, the energy is given. Formula for energy is E is equal to hc by lambda. Now we know that Planck's constant h is given by 6.67 into 10 to the power minus 34 into 3 into 10 to the power 8 upon lambda is 6.328 into 10 to the power minus 7. When you solve, you will get 3.129 into 10 to the power minus 19 joules. But answer we always write in terms of electron volt, so we need to convert joules into electron volt. And the formula is 3.129 into 10 to the power minus 19 divided by 1.6 into 10 to the power minus 19, and it will give you 1.956 electron volt. Now next we need to find the momentum. So momentum of the photon is given by h upon lambda. Again Planck's constant is known, so you need to remember this value of Planck's constant, which is equal to 6.67 into 10 to the power minus 34. We will substitute over here, divided by lambda. Lambda is already given, 6.328 into 10 to the power minus 7. So answer is 1.043 into 10 to the power minus 27, and the unit is kg meter per second. Next numerical is the coherence length of sodium line of wavelength 5890 angstrom degree is 2.5 centimeter. So what is given? Coherence length, that is 2.5 centimeter, and wavelength they gave lambda is equal to 5.890 into 10 to the power minus 7 meters. Calculate the coherence time, half width of the spectral line, purity of the spectral line. Given L is equal to 2.5 centimeter is equal to 2.5 into 10 to the power minus 2 meters. We will convert everything into SI system. Then lambda is equal to, as I told, 5890 angstrom degree, we need to convert it into meters. So 5.89 into 10 to the power minus 7 meters. C is equal to 3 into 10 to the power minus 8 meter per second. First we need to find the coherence time, which is denoted by tau, and the formula is length upon C. So 2.5 into 10 to the power minus 3 divided by 3 into 10 to the power 8, which will give you 8.3 into 10 to the power minus 11 second. Half width of spectral line del lambda is equal to lambda square upon L is equal to 5.89 into 10 to the power minus 7 upon 2.5. L we got, L is given 2.5 into 10 to the power minus 3. So 1.4 into 10 to the power minus 11 meters. Now last we need to find the purity of spectral line. Q is equal to lambda upon del lambda. Lambda is 5.89 into 10 to the power minus 7, and del lambda is equal to 1.4 into 10 to the power minus 11, which you will get The answer is 4.2 into 10 to the power 4. That is the purity of spectral light. The fringes of Michelson interferometer are clearly visible with that of HE-NE laser, till the difference in path between the two interfering waves is increased up to 8 meter. If the wavelength of the laser beam is 11.5 into 10 to the power minus 7 meter, then calculate the coherence length, coherence time and purity of spectral light. So here they gave us length, that is 8 meter. We know velocity of light is 3 into 10 to the power 8 meter per second. So first we can find the coherence time. It is denoted by tau is equal to L upon C is equal to 8 upon 3 into 10 to the power 8 is equal to 2.67 into 10 to the power minus 8 second. Then we need to find the half width of spectral line. Del lambda is equal to lambda square upon L is equal to lambda is given 11.5 into 10 to the power minus 7 meter. It is already given in meter, so there is no need to change into SI system. It is already in meters. Divided by length is 8, and half width of the spectral line we will get as 1.65 into 10 to the minus 3 meters when we solve. Then we need to find the last is purity of spectral line. Q, it is denoted by Q is equal to lambda upon del lambda is equal to 11.5 into 10 to the power minus 7 divided by 1.65 into 10 to the power minus 13, which will give, you will get 6.97 into 10 to the power 6 is the purity of the spectral line. If light of 6000 Armstrong degree wavelength has wave train 20 lambda long, what are its coherence length and coherence time? So length of the train is L is equal to n times lambda, which they gave you 20 into lambda. So coherence length is equal to 20 into lambda. So when you will do 20 into 6000 into 10 to the power minus 10 meters, when you solve that you will get the coherence length. There is a printing mistake, so here 20 multiplied by 6000, you need to do 6000 Armstrong or convert it into SI system. When you convert it into SI system, then it comes 20 into 6000 into 10 to the minus 10 meters. Now we need to find the coherence time. Tau is equal to L upon C, which is equal to 20 into 6000 into 10 to the minus 10, that is the L coherence length, divided by C, velocity of light. And remember this, velocity of light is 3 into 10 to the power 8 meter per second. So when you substitute and when you solve, you will get 0.4 second. A laser beam has a wavelength of 8000 Armstrong degree and aperture is equal to 5 into 10 to the power minus 3 meter, and we need to calculate the angular spread of the beam. So what is given? Lambda, that is 8000 Armstrong degree, and that is nothing but 8 into 10 to the power minus 7 meters. And the aperture they give us, that is small d, is equal to 5 into 10 to the power minus 3 meters. Now angular spread of the beam is given by, is denoted by del theta is equal to lambda upon d. So lambda is 8 into 10 to the power minus 7 divided by d is 5 into 10 to the power minus 3 meters, which will give you 1.76 into 10 to the power minus 4 radians when you solve. Find the intensity of the laser beam of 10 milliwatt power and having a diameter of 1.3 mm. Assume the intensity of the uniform cross section of the beam. So here it is given power P is equal to 10 milliwatt is equal to 10 into 10 to the minus 3 watt. Diameter D is equal to 1.3 mm is equal to 1.3 into 10 to the power minus 3 meters. Now intensity I is equal to power upon area is equal to 4 into 10 to the power minus 3 watt divided by area. Area is pi r square. Therefore pi into 1.3 into 10 to the power minus 3 the whole square. So you will get, when you solve, you will get 7534 watt per meter square. That is nothing but 7.5 kilowatt per meter square. Since diameter is given, that's why we took area in terms of pi. A laser beam can be focused on an area equal to square of its wavelength. For HE-NE laser, wavelength is 6328 Armstrong degree. If the laser radiate energy at a rate of 1 milliwatt, find out the intensity of focused beam. Given lambda, wavelength lambda is equal to 6328 Armstrong degree is equal to 6.328 into 10 to the power minus 7 meters. Then power P is equal to 1 milliwatt is equal to 10 to the minus 3 watt. Now area A is equal to lambda square. Here they are not, here they told directly it is a square. So that is length square, that is wavelength square, lambda square, which is equal to 6.328 into 10 to the power minus 7 meter square is equal to 40 into 10 to the power minus 14 meter square. Make use of calculator. Calculator is allowed in the exam. Intensity I is equal to power divided by area is equal to 10 to the power minus 3 divided by 40 into 10 to the power minus 14 meter square. That is 2.5 into 10 to the power 15 watt per meter square. White light has frequency range of 0.4 into 10 to the power 15 hertz to 0.7 into 10 to the power 15 hertz. Find the coherence time and coherence length. Coherence time tau is equal to L upon del mu. So tau is equal to L, it is given over here 1 because it is frequency range. They gave us frequency. So del mu is nothing but difference in the frequency. Therefore 0.7 minus 0.4 into 10 to the power 15. Remember, when frequency is given, then you should take length is equal to 1 per unit length, like that. So you will arrive to coherence time tau is equal to 3.33 into 1 into 10 to the power minus 15 second. It is again one correction is there. It is not 110. It is a 10 to the power minus 15 second. Now coherence length L is equal to C into tau C. So we know that tau we just now got 3.33 into 10 to the power minus 15 meters and seconds, and C is equal to 3 into 10 to the power 8. Therefore coherence length, when you calculate, you will get 9.99 into 10 to the power minus 7 meters. Sodium atom radiates for 4 into 10 to the power minus 12 second. What is coherence length of light from a sodium lamp? So what is given? Given is coherence time tau is equal to 4 into 10 to the minus 12 second, and we need to find the coherence length. L is equal to tau C. We know that C is equal to 3 into 10 to the power 8 meter per second, and tau is 4 into 10 to the power minus 12. When you substitute, you will get 1.2 into 10 to the power minus 3 meters. Now this question appears little bigger, but in examination there are chances they can divide the question and they can ask a small portion, either one or part 2 they can ask. So the ruby laser has two states of 3000 Kelvin and 5000 Kelvin. If it emits light 7000 Armstrong degree, then calculate relative population. So what is given? Temperature T1 is equal to 300 Kelvin, T2 is equal to 500 Kelvin, and wavelength lambda is equal to 7000 Armstrong degree. We will convert Armstrong into meters. So it is 7 into 10 to the power minus 7 meters. Ratio of population of two states at temperature T is given by N2 upon N1 is equal to e to the power minus del E upon kT, where del E is equal to hc by lambda. Now first, relative population of the two states at T1 is equal to 300 Kelvin. Therefore del E is equal to 6.63 into 10 to the power minus 34 into 3 into 10 to the power 8 divided by 7000 into 10 to the power minus 10, which will give you 2.84 into 10 to the power minus 19 joule. So del E upon kT is equal to 2.84 into 10 to the power minus 19 divided by 1.38 into 10 to the power minus 23 into 300, and you will get 68.59. Now we need to find the ratio of the population of the two states. N2 upon N1 is equal to e to the minus del E upon kT. So E upon kT is 68.59 just now we found. Therefore N2 upon N1 is equal to e to the power minus 68.59. So you will get 1.67 into 10 to the power minus 30. Now ratio of population of the two states N2 upon N1 is equal to 1.62 into 10 to the power minus 30, and relative population of the two states is when temperature is 500 Kelvin. So we need to change it to 500. We will replace by T by 500. So del E upon kT is equal to 2.84 into 10 to the power minus 19 divided by 1.38 into 10 to the power minus 23 into 500, which will give you 41.15. So same as the procedure we did for the part 1, same N2 upon N1 is equal to e to the power minus 41.15, which will give you 1.34 into 10 to the power minus 80. Find the ratio of population of two states in HE-NE laser that produce light of wavelength 6328 Armstrong degree at 27 degrees Celsius. So what is given here? Temperature is given, T is equal to 27 degrees Celsius. We will convert it into Kelvin. So 27 plus 273 will give you 300 Kelvin. Wavelength lambda is equal to 6328 Armstrong degree is equal to 6328 into 10 to the power minus 10 meters. Now energy difference del E is equal to, we know the formula, del E is equal to hc by lambda, where h is Planck's constant, c is velocity of light, and lambda is the wavelength of the laser beam. So h is Planck's constant, so 6.63 into 10 to the power minus 34. C is velocity of light, 3 into 10 to the power 8 divided by lambda. Just now we got 6328 into 10 to the power minus 10 meters, which is equal to 3.143 into 10 to the power minus 19 joules. Now ratio of population of the two states at temperature T, Kelvin, is given by N2 upon N1 is equal to e to the power minus del E upon kT. Therefore minus del E upon kT is equal to 3.143 into 10 to the power minus 19 divided by 1.38 into 10 to the power minus 23 into 300, which is equal to 75.92. And we need to find the ratio of the population, that is given by N2 upon N1 is equal to e to the power minus del E upon kT. So when we substitute, so we will get N2 upon N1 is equal to e to the power minus 75.92, which is equal to 1.067 into 10 to the power minus 33. Therefore the ratio of population of the two states N2 upon N1 is equal to 1.067 into 10 to the power minus 33. Now we are going to find the light of a certain wavelength has wave train 13.2 into 10 to the power minus 2 meters. Calculate the coherence time. So what is given? Here it is given L. Coherence width L is equal to 13.2 into 10 to the power minus 2 meters. So coherence time tau is equal to L by C, which is equal to 13.2 into 10 to the power minus 2 divided by velocity of light, that is 3 into 10 to the power 8. And you will get coherence time tau is equal to 4.4 into 10 to the power minus 10 seconds. Now we are going to see, in a laser action due to transition from the excited to the ground state, a beam of wavelength 6930 Armstrong degree is obtained. Assuming the energy of the ground state to be 0, find the energy of the excited state. So we know the formula, E2 minus E1 is equal to hc upon lambda, and here they give ground state, so E1 is equal to 0. Therefore E2 is equal to hc upon lambda. Substitute the value of Planck's constant h, that is 6.63 into 10 to the power minus 34, and c is velocity of light, 3 into 10 to the power 8, and lambda it is given 6930 Armstrong, that we will convert it into meters, 6930 into 10 to the power minus 10. And when you solve, you will get answer in terms of joules, 2.857 into 10 to the power minus 19 joules, and then we need to convert it into electron volt, that is 2.857 into 10 to the power minus 19 divided by 1.6 into 10 to the power minus 19 electron volt, which will give you 1.786 electron volt. Now we are going towards problem number 50. In a laser system, there are only two energy states of atom, in which the energy difference is equivalent to the radiation of frequency 4.7 into 10 to the power 14 Hertz. At an absolute temperature 300 Kelvin, compare the number of atoms in this energy state. Here we need to find the ratio of N2 upon N1. So the ratio of the population of the two states at temperature T is given by N2 upon N1 is equal to e to the power m minus E2 minus E1 upon kT, where E2 minus E1 we write as del E is equal to h nu. So e to the power minus h nu upon kT, where h is Planck's constant, nu is frequency, k is Boltzmann constant, and T is temperature. When you substitute, you will arrive e to the power minus 74.9, and when you solve e to the power minus 74.9, you will get 2.96 into 10 to the power minus 33. Now we are going to solve. Find the ratio of the population of the two states in a HENE laser that produce light of wavelength 6328 Armstrong degree at 27 degrees Celsius. So wavelength of the light is equal to lambda is equal to 6328 Armstrong degree is equal to 6328 into 10 to the minus 10 meters. Temperature T is equal to 27 degrees Celsius. We will convert it into Kelvin. So we need to find the ratio N2 upon N1. Energy difference Delhi is equal to minus Hc upon lambda, and the ratio of the population of the two states is equal to N2 upon N1 is equal to e to the power minus Delhi upon K2. Therefore, Delhi is equal to 6.63 into 10 to the power minus 34 into 3 into 10 to the power 8 divided by 6.328 into 10 to the power minus 10. When you solve, you will get 3.143 into 10 to the power minus 19 joule, but we will get joule, you can keep it as it is, and now substitute Delhi upon KT. So 3.143 into 10 to the power minus 19 divided by K is 1.38 into 10 to the power minus 23 into 300, you will get 75.9. Therefore, N2 upon N1 is equal to e to the power minus 75.9. You will get 1.1 into 10 to the power minus 33. So the ratio of population of the two states is N2 upon N1 is equal to 1.1 into 10 to the power minus 33. Now we are going to moving towards the next problem, that is a sodium atom radiates 4 into 10 to the power minus 12 seconds. What is the coherence length of the light from the sodium lamp? So given coherence time t is equal to 4 into 10 to the power minus 12 seconds. Coherence length we need to find. Therefore, L is equal to C into tau. L is equal to 3 into 10 to the power 8 into 4 into 10 to the power minus 12, which will give you 1.2 into 10 to the power minus 3 meters. So coherence length is equal to 1.2 into 10 to the power minus 3 meters. Now we are going to find which is the following is a unique property of laser. It is direction, speed, coherence, wavelength. So unique property here it is coherence. When a laser light is focused on a particular area for a long time, then that particular area alone will be heated, true or false? That is true. Calculate the wavelength of radiation emitted by an LED made up of semiconducting material with a band gap of 2.8 electron volt. The answer is 2.8 Armstrong, 4.3308, 5548.4 Armstrong degree, 4430.8 Armstrong degree. So answer is in the second slide. Formula is E is equal to Hc upon lambda. H is Planck's constant. C is velocity of light. When you substitute, you will get 4430.8 Armstrong degree. Next problem is what is the need of what we will need to achieve population inversion. So in order to find the population inversion, means population inversion here means number of atoms in the excited state is more compared to number of atoms in the ground state. So we need to excite most of the atoms. That is the correct answer, to excite most of the atoms. Means DVD uses laser, true or false? Yes. DVD is operated with the help of laser. When a laser beam touches its surface, then you can listen or listen the music, etc. can be done. So yes, DVD uses laser beam.